Today, I want to talk about this, dynamic locomotion in humans, animals, and robots. And if you think about this, this is a very bad title. It's not catchy, it's super generic, this could be anything. So in preparation for this talk, I thought about a better title, something that's a bit more catchy. Here it is. Why is going to IKEA with Julia so exhausting? And this is only partly a joke, because what I was trying to tell you today, or what I was trying to do today, is give you some scientific evidence why going to a museum or shopping with your partner, we move along very slowly through some space, is so much more exhausting than going for a nice hike in the woods. And I hope if you forget everything, you might remember this one part of this talk. I'm a roboticist. I study locomotion with a goal to build robots that walk, that run, and to also build robots that help humans to walk and run in terms of rehabilitation engineering. And like everybody in this field, I'm amazed by videos like this. If you look at what nature can do, right, this agility, the speed, the grace, right, and then you compare this to what we can do with robots, there's such an obvious challenge to make machines better, to figure out the hardware, the design, the actuation, the controls, just to at some point reach a level of performance that we see in everyday life, and that we ourselves, right, we're all very good in walking as long as we don't try to do it with robots. Something that amazes me particularly about looking at locomotion in nature is that it comes in such a big variety. These are animations made of photographies done very early on. Edward Muybridge made these, the pictures that are the base for these photos. He made those in 1887. And they show us that there's a large variety of different modes of locomotion. Within one species, we have horses that walk, trot, gallop. You have different morphologies, different species of animals, elephants, camels. You have a bison galloping there, and then we have two bipeds, one we know very well. And then there are these other more silly ways of locomotion. And a lot of my research revolves around this question, where are these different modes coming from? Why are we doing this? Why are they useful? And is that something that might be useful for robotics? And this is sort of a two-way game, right? We are trying to learn from nature, learning from biology, and at the same time, as we do this, we might learn something about nature. At the moment, we're trying to build our robots. How do gaits differ, right? I said these are very obviously different modes of locomotion, but what is different about them? And there are two things. The first thing is they have different footfall patterns. And you might know this, that, for example, in a walk, the 4 feet strike the ground in an evenly sequence. If we look one below, the trot, diagonal pairs of legs strike the ground at the same time. And we normally represent these footfall patterns in these diagrams where we say this is where feet strike the ground or are on the ground. So for a trot, for example, we would start with 2 diagonal pairs of legs on the ground. Then we have an air face here where no leg is on the ground, and then the other pair of legs is on the ground. This is one way of distinguishing different gaits, but then if we look more closely, not only at the time or the moment when a foot hits or leaves the ground, but look at the forces that these feet produce, we can extract these force profiles. This is basically the force that a foot puts on the ground as it's putting weight, or as the animal is putting weight on this foot. And gaits differ in both, right? If you go from the top, walking, trotting, galloping, you see there are different footfall patterns, but there are also different shapes of these ground reaction forces. Particularly if you look in the top right corner, you see that during walking, during slow gaits, we have sort of an M-shape or double hump ground reaction profile. And then for the faster gaits, running and galloping, there's just a single hump or a single peak that we see. Now, these animations that I'm showing you, they're actually based on a bet that is directly related to this idea of footfall patterns and different gaits. Because back when Edward Muybridge took these pictures, people actually didn't know in which sequence horses would strike the ground with their feet. And they actually believed that during trotting, as you can see here, there's always at least 1 foot off the ground. So basically, this air phase that we see here in the center was, you know, they didn't believe that would exist. Whereas in galloping, they were believing that there are actually 2 air phases, one with the feet gathered, and then a second one, as you can see this on this picture from 1820, where the feet are stretched out in the front and in the back. And Leland Stanford, the governor of California in that time and founder of Stanford University, he had a $25,000 bet that this was wrong, that horses do not have the feet in the air like it is shown here, and galloping and in trotting, that they actually come off the ground completely and have an air phase. So he asked Edward Muybridge, a known photographer, if he could show some proof of that. And that, you know, was a time when basically making a photo means that you stand there, someone opens a shutter, someone closes a shutter, and in the meantime, you better not move. Because if you move, your photo gets blurry. Now, that is a bit of a problem when you're trying to take a photograph of a galloping horse. So he had to make, you know, actually 2 interesting inventions, and is basically the inventor of stop motion photography or of slow motion videos, right? Where he said the first thing was I have to automate that process of opening and closing the shutter. And this should happen very quickly. And he had a very simple trick. He took a wooden board, cut a hole into it, and just had the board fall with the hole fall past the opening of the camera. So this would open and then close again as the hole has passed the camera opening. That was one thing, right? So he could take pictures with very short exposure times. But then he also had to trigger it to the motion of the horse. And this was even a more genius idea where he said, well, I just take a line or piece of string across the racetrack, connect that to the falling board. If the horse passes it, it pulls on the line. The wooden board falls. I take one picture. And then he took 12 cameras, put them next to each other with 12 lines running across the racetrack. And as the horse passed, one after the other would take a picture. And that would give him a series of photos, as you can see them here. And you can see that for this galloping gait, right, we have one phase where all the legs are in the air, shown here, but that during the phase where the legs are extended, there's always at least 1 foot, right, sometimes even 2 feet in the air. So Stanford won his bet, and we now, 130 years later, have these wonderful pictures, and then people turn them back into animations and movies. Now, why different gaits, right? That was the question that I raised at the beginning of the lecture. And the answer is closely related to a question of energy consumption. And this is my absolute favorite figure. And I will basically only talk about this figure today. It's based on a simple experiment where Hoyt and Taylor in 1980, they took a horse and put it on a treadmill, set the treadmill to a certain speed, and then measured the amount of energy that the horse was using by measuring the oxygen that it took in and the oxygen that it was breathing out. And the difference between that allows you to figure out how much energy or how much calorie stores is burning, how much energy it is using. And based on that, they created a figure that on the one axis just shows the locomotion speed, the speed of the treadmill. On the y-axis, they show the amount of energy the horse uses per distance traveled. So not just the amount of energy, but normalize that by the velocity that you get, basically units of energy per distance, right? If we go for a hike, that's maybe the amount of cliff bars that we need to cover a mile. In Europe, this is how cars are rated, right? We say, oh, this car needs 8-liter gasoline per 100 kilometers. And then he just put the measurements that he took, or they put the measurements that they took into this graph, and they had a horse walking, and it gives us this nice, almost parabolic shape. If the horse was trotting, you get a second parabolic shape at a higher velocity. It's a faster gait. And then for galloping, you don't see quite the same parabola, but you can imagine if you go to even higher speeds, this might curve up or not. We don't know. So that was one part of the experiment, just measuring how much energy it takes you to move at a certain speed. And it's kind of interesting to see that, intuitively you would think going faster always costs you more energy. But since this is normalized by distance, going faster means you're covering a larger distance. So if I normalize it back by distance, I end up with these graphs that actually tell me going at a slower speed, right here, takes more energy than going at a medium speed. And then if I go faster again, I increase my energy consumption. And at some point, right, these two lines would cross. And it makes sense energetically to switch to a trotting gait, which then has lower energy consumption as a minimum here, and then the same game starts again. So in the second part of the experiment, all they did was they went out to the pasture where they were having their horses at the Concord Field Station and just looked at them and kind of recorded at what velocity they normally would locomote. And they just recorded observations if that locomotion velocity falls into a certain speed range. And then they plotted this for walking, trotting, and galloping. And you see that horses tend to locomote at exactly the minima of these energetic curves. Other people have repeated these experiments. If you have a trash can and a lot of duct tape, you can do this for larger quadrupeds. You can do this for primates. You can do this for slightly smarter primates. And then for humans, we get a similar idea, right? We have this curve that has a clear minimum down here. And then if I go faster or slower, my energy consumption to travel a certain distance goes up. And we are aware of that. What is marked here as the natural speed that is the walking velocity that I would choose if someone just tells me, can you walk across the room? And of course, that is super useful because at that velocity, I minimize the energy, right, that I need to cover a certain distance. So this is great. Whereas if I'm forced to go slow, for example, because I'm in an IKEA, my energy consumption almost doubles, right? And again, I need twice the amount of energy to cover the same distance. That's about, I think if you go through IKEA, it's about 1 mile, and this is where you get the meatballs. So, and I'm pretty sure you're smart people. Some of you have already seen this in this figure, but the only relation of horses and IKEA is through these meatballs. And I think they fixed that issue, but that's why I didn't want to put it in this figure. Now, interpreting this graph seems simple, right? There are these minima, and obviously the horses are aware of these minima, and then they locomote at exactly those speeds, right? Anybody objects this? Is everybody seeing this? Yeah, no objections? Good, you're all wrong. You're not. No, the reason, and this is one of the largest pitfalls in science, is to mix up causality and just that two things happen at the same time, right? Just that minima and preferred locomotion speeds correspond, right? We have this correspondence. Doesn't mean that one follows from the other. I can say, well, horses walk at these velocities because that's where it's most efficient. But you could turn it around and say, well, there's for some reason horses like these locomotion velocities. They have been locomoting at these speeds all their life. Of course, they're better at doing it, right? If all of a sudden you force them to go faster or slower, they don't know how to do it, and energy consumption goes up, right? So we cannot directly follow causality just from this figure itself. And this is the part where I want to talk about if we try to do things in robotics, we might actually learn something about nature. I'm trying to build robots, and before you build a robot, you normally start with a model. And we have these zoo of models, which are kind of conceptual, but you can see that they resemble something technical. There are springs here, and the springs are actually driven by what we call a series elastic actuator, or the robots are driven by a series elastic actuator, where these actuators are basically sitting at the top of the spring, so you can inject energy into the system, and at the bottom you have a joint which is compressing against the spring. We will see a lot of videos of this, and then this idea becomes a lot clearer. What has this to do with horses? Right, technical system with springs, but if you go through the literature and you look at how horses are constructed, their muscles, their tendons, everything is soft, and the elasticity in your tendons and your muscles actually makes a horse leg behave almost like a spring. Now, with these models, what we wanted to do was to create locomotion. And creating locomotion means, first of all, figuring out what is locomotion. Right? What does it mean to locomote? And the answer is simple, right? I go from here to over here, and that was locomotion, right? I have an average velocity for move. But I could do all different kinds of locomotion, right? I could do this, and I would equally locomote over here. And then I'm pretty sure you've all seen these funny videos from Monty Python, the Ministry of Silly Walks. So there are all kinds of, of ways of going from one point to another. That is, for mathematical definition, if you want to create a gate, that is not the best thing to do. But even in these super silly gates, there's a pattern. Most of these gates are periodic, right? So there's something inherently periodic about locomotion. And that is something that we can use to our advantage if we're trying to recreate locomotion in a computer. Because if I do something periodic, it means I do something, starting at a certain position, I do something, I end up in the same position, and whatever it was I did, I can do it again, and again, and again, and that moves me forward. Which means that instead of studying the entire motion across the room, all I have to do is I study one stride, and then say, well, if you can do this, then you can locomote. So we formulated that requirement that you have to move forward and create something periodic. We formulated this as constraints in an optimization problem, which means we required a computer to find a motion that is moving us forward and that is periodic, and that, obeys the laws of physics. There are constraints. You cannot move your legs through the ground. You have actuator limits. Things might break. These dynamics are governed by Newton's law. So we have these laws of physics, and we can implement them in a computer. And that gives us a set of constraints, right? To find a motion that brings you forward, that is periodic, and that obeys the laws of physics. And we've just seen that. There are infinitely many ways to do that. A lot of them are silly, and Monty Python only showed you a few of them. So to find one specific motion, we have to add something, and that is adding the requirement that the motion should be energetically economic. So of all the possible gates, including the Monty Python ones, we are trying to find the ones that are most efficient. We implemented this as a constrained nonlinear optimization problem in a computer and asked the computer to find such a gate. That is equivalent of finding an optimal limit cycle, and this is a bit technical, so we'll rush through this, but the basic idea is the same. If I have a periodic motion, I go through the same configuration once every stride. And I got back to this configuration. If I represent the configuration as speeds and angles of my joints, I can create numbers, and these numbers change over a stride, but these numbers have to form something periodic. I'm coming back to the same point, and I'm doing the same thing over and over again. So it creates, in the state space, in the mathematical description of our motion, it creates this periodic orbit. And then we say, well, I don't want to look at this orbit. That looks awfully complex. But if I just look at the motion once every stride, shown here by this plane, which represents I'm at the highest point of my arc, and I only look at the motion at that point, the problem becomes fairly simple. I have to find a fixed point in which I hit the same configuration once every stride. And if I don't do that, as shown in the last sort of circles of that orbit, then I don't have a periodic solution. So green dot, periodic solution, the other two dot, a non-periodic solution. We describe this through a large number of parameters, hundreds of numbers, and then just throw a computer at it that plays around with these numbers and tries to figure out the best combination, which means the most energy efficient gate. Gate in the sense, something that moves me forward and is periodic. If we do this for slow velocities, the computer tells us that with the model that we give it, we should do this. And that looks awfully close to walking. And that is remarkable because the computer has no idea what walking is, right? We didn't tell him anything about walking. The computer could have came up with any of the Monty Python gates, but it chooses something that looks very, very close to human walking. If we look at the contact sequence, we see that there's a time here where both feet are on the ground. I'm sorry. We have these ground reaction forces shown here that have the M profile that we saw before when we looked at walking horses. So this looks very, very close to human walking. And then we asked the optimizer, now can you do the same thing at a higher speed? So we increased the speed. And I have to apologize for this video because this is now a slow-mo video. So time has been slowed down, so this looks actually slower than the previous one. But you have to believe me that this is a higher speed, just played back at a slower velocity. And that looks like running, right? And if we look at the ground reaction forces and at the contact pattern, the computer actually figured out that makes sense to have an air phase, and that my ground reaction forces now only have the single hump. So that was pretty cool, right? The computer doesn't know anything about locomotion apart from what I told him, or what I told it, and it comes up with these solutions. In between, we found something interesting, where we have the ground reaction forces of running, a single hump, but we have an overlap here. So we have a double stance phase, right? During walking, there's this phase where I have both legs on the ground, and I have one leg, two legs, one leg. Whereas in running, it would be one leg, being in the air, then the other leg. Oh, that was bad. Right? With an air phase in between. So we have the ground contact pattern of walking, and we have the force profile of running. And we thought, okay, that's just because we have this weird model, and humans never do that. And then we showed this to our colleagues in kinesiology, and they said, well, humans, you can make humans do this. If you take a very heavy backpack and put it on, a human subject and ask it to run as fast as possible, they will do this. They will try to run, but they won't get both feet off the ground. So it was kind of fun to see that, you find this by chance, and then someone tells me that it's something that actually exists. And then if we continuously vary velocities and plot here the cost of transport, assuming that there's also some sort of basic offset cost in the locomotion, and this is again the same graph that I showed you before, cost of transport over speed, you see that this transition from walking to running is driven through energetics. At low velocities, walking is the most efficient gait, and then at this point, all of a sudden, it makes sense to have an air phase, and at higher velocities here, running is the most efficient gait. We then got ambitious, played around with quadrupedal models, then we made walk, The 2-beat walk, that is actually something artificial that so far we haven't seen in nature, but I'm pretty sure sometimes I give this talk and someone will say, oh, there's this breed of horses that do exactly this. We can do tilting on the left side. That's a gait that Icelandic horses are doing. We can find trotting, which is the more common medium speed gaits. And then we looked at bounding, sort of the motion that a squirrel does, and then galloping, which looks still a bit awkward. And I create the same graph, right, where I vary my forward velocity, measure the cost of transport. And this is equivalent now to this Hoyt and Taylor figure, right? So this is my version, my robot model optimization-based version of the Hoyt and Taylor experiment. And you see that there are striking similarities, right? What we have is that for every gait, right, shown for walking, for example, here 4-beat and this weird 2-beat walk, we have an optimal locomotion speed. So if you choose walking for a robot that looks roughly like our model, you should locomote at that velocity. If you're trotting, right, an optimal gait would be somewhere here. And as you change your velocity, at this point, I should also change my type of gait, because otherwise I will end up on this line here and will, well, just waste energy. There are also some differences, right? You see that our galloping gait in this particular study, and it looked a little bit awkward, but that galloping gait is never more efficient than any of the other gaits. That raises an interesting point, right? Before we said we didn't know what was first, right? The horses liking to locomote at a certain velocity, leading to these curves, or these curves forcing the horse to locomote at a certain velocity. Now the answer is clear, because the graph on the left was generated in a computer which had zero preferences for anything, just tried to find the best way of locomoting at every speed. It tells us that there must be something fundamental that is causing these energetic relationships. And that fundamental thing can only be the laws of physics, right? Because that's the only thing that we put into our model. We said you should move forward, should be periodic, but you have to obey the laws of physics. So the laws of physics are causing this, the mechanical dynamics. And we call this the mechanical natural dynamics in the system. They are driving the motion, and they're driving these energetic curves. Natural dynamics is a very generic term, right? Natural dynamics, if you Google that, if you put this in Google Scholar, you look for natural dynamics, you find papers about the natural dynamics of the unemployment in the US. You find papers about the natural dynamics of coastlines in the Netherlands. But it always means sort of the same thing, the behavior that a system, that something exhibits without external intervention. Now, this is a robot, or at least a model of a robot. So the only thing that can happen is driven by mechanics, that is, by the interaction of inertia, of gravity, and of elastic oscillations. And here are 3 examples of particularly useful dynamics in locomotion. The first is a simple pendulum. And we use a pendulum, and I show this here. A pendulum like this, right? It's an inverted pendulum. So I set this into motion, oops. And it just moves by itself, sort of vaults like a pole vaulter. Once set into motion, it passively moves forward. And this is what happens in walking with our stance foot. I put my stance foot on the ground, and I just fall forward. Like an inverted pendulum, my center of mass is around here. I fall forward, and that moves me forward. At the same time, I have to get my swing leg, my second leg, forward. Now this, again, can be seen as a pendulum. but this now is a pendulum with 2 segments. So it's a double pendulum, as it is shown here. So I have my leg somewhere back here, and if I let this go, it will swing forward. If you look closely, and I show you this first, in order that you know what you see, is that this is not just swinging forwards in a straight line, but this actually bends a little bit and then extends again. And that is necessary because if I swing my leg forward in a straight line, I'll scuff my foot. So I have to bend my knee and retract that and then extend again so I can clear the ground. Let's see if you can see this. This is happening a bit fast. I'll show you a couple of times. So I move forward, and at the lowest point, the knee is bent, and then it extends again. And now you can imagine if I get the properties of these 2 dynamical systems right, I can actually get the forward motion as an inverted pendulum passive, and I get the swing leg motion passive, and if they're timed the same way, the moment I need that foot to be here, it will be there, and then I just switch the roles of these 2, and I just basically fall forward without doing anything. The third picture shows a third kind of mechanical oscillations and mechanical dynamics that we get, which is simply the motion of a spring, right? We talked about this, that muscles, that tendons, that they are all elastic, they can store energy, and then create these oscillations or these additional dynamic motions. That has interesting consequences. If I do an experiment where I take one of you and put him on a treadmill, and that person is walking, you would think, well, that is a motion that involves a lot of joints, right? Every joint is moving. My arms are moving, my legs are moving. You know, if I'm happy, even my head is moving. But if I put electrodes, EMG electrodes on your muscles and measure your muscle activity, I would see that there's not a lot going on. So it's these mechanical dynamics that are driving the motion. It's not the muscles. My arms are not swinging because I'm swinging them actively. It's just because they follow sort of their natural pendulum motions. Realizing that, scientists came up with these incredibly impressive machines. They're called passive dynamic walkers. And they can walk without actuators, without sensors, without anything. They're walking down sort of a small incline. They have to be powered some way, so they're powered by walking downhill. But there are no actuators, there are no sensors. And they're based on, on toys that go back, 80 years. People came up with these walking toys. And then Ted McGeer, who is showing this video, created this
Oh, God!
And it mimics a human walking motion. No actuators, just driven by the natural dynamics. And then others picked up. I wanted to show you this video because this is the guy who kind of came up with this design. Here you can see it a little bit better. 16 years later, the video quality has improved. This guy is walking passively for 35 minutes. And it's walking, on this incline treadmill that keeps it going, that powers it. And the video below that shows that this motion is very similar to human motion. And I want to demo a cheap version of such a passive dynamic walker here. This one, I have this from TU Delft, doesn't have knees. So I have to play a little trick to generate foot clearance, which is why I have these pads. So you're always stepping on a pad and then swinging through essentially one of these holes, stepping on the next pad, swinging through a hole. And I should warn you, these are horribly difficult to start. So in the videos that I just showed you, in their paper, they claim they did 450 trials before they had their 35-minute success. And the way McGeer celebrated, you could see that it took him a while to get it started because you have to hit exactly this limit cycle. So I give this a try. That was not too bad. And if you want to, you can try it later after the lecture. Come here. Yeah. Oh yeah, good enough. I had a video in case this fails. And then I want to share this with you. This is a machine that is built on this principle and currently holds the record for walking distance by a robot. So this walked 63 kilometers on one battery charge, 1.5 marathons, and heavily exploiting these natural dynamics that I just showed you. So it's super efficient because the natural dynamics are doing all the work, and all you have to do is to compensate a little bit for friction and collision losses. Now, can natural dynamics, as I just showed you, can they explain the existence of multiple gates? And we were wondering this, and we took, to answer that question, we took our models and made them even simpler. We said, well, to create such a passive walking motion, you either have to walk to on a ramp to compensate for energetic losses, or, there's a model, so let's just make the model that it doesn't have any losses. So we said, these springs are perfect. They don't have any damping. There's no friction. The springs don't have a mass, so we don't have to think about collision losses. And we get this super simple system, which is essentially just a stick, right, a box on 4 springs. And every time a spring is in the air, we just assume it goes to a predefined, what we call angle of attack. And since it doesn't have a mass, that is a simple assumption, just goes there and waits till it hits the ground again. Otherwise, this model is completely passive. No actuators, no sensors, nothing. So it just depends on how you start it, what kind of motion it will create. It turns out, if you start it right, you can create a trotting motion. You can create a pace. These are very similar. The only difference between a trot and a pace is that in a trot, diagonal pairs of legs are active at the same time. And in the pace, the legs on the same side of the body are active at the same time. Horses normally trot, camels pace. The reason why they pace is because they have so long legs that they would interfere if they would try a trot. If we increase the speed, if we try other ways of starting the model, and it's still the same model, simple passive model, we can make it walk, and we can create this tilt, this gait that Icelandic horses are using. And that is awesome, right? I just showed you that 4 quadrupedal gaits are just the consequence of a stick on springs. At least in terms of of the contact patterns, but also qualitatively in terms of the ground reaction forces, right? You have this M shape here for walking, for tilting, and the other running gaits, you have the single hump. So we called up our friends at the veterinary clinic in Zurich, where they have a treadmill for horses, an instrumented treadmill where they can actually measure these ground reaction forces, and compared our results to theirs, and then changed our model parameters, mass, mass distribution, main body length, and so on, to sort of optimally match their results. And what you see here is a nearly perfect agreement between trotting in our model, which again is just a stick on a spring, and trotting in actual horses. For tilting, it's the same, almost perfect. Walking, we're not fully there yet, but sort of bulk part, we can almost recreate that exact same ground reaction forces. And then we played around a bit more. Can we do more gaits? We found that we can do bounding completely passively. We found that we can do a galloping gait, as it's shown on the right, completely passively. So locomotion is driven by these mechanical dynamics, very simple dynamics, and we can do different gaits. What are different gaits, right? Where are they coming from? And just comparing these 2 figures, or these 2 animations, you see that they're essentially just 2 different modes of oscillation of this mass on a spring. If you look closely in walking, the spring compresses, extends, compresses again, and then extends as it is on the ground. So I get compression, extension, compression, extension. This is called the mid-stance relief, the extension in the middle, and that leads to these M-shaped ground reaction forces. In trotting, the spring compresses once and extends again, which results in the single hump ground reaction forces. So we can generate different oscillation modes in a very simple model, and these different oscillation modes correspond to different gates. So a way of interpreting this figure is to say that each of these gates, each of these three lines, is a different oscillation mode. Now, why do they have this shape? Well, this comes from this idea of resonance. If I have an oscillator, like this one here, it has a certain natural frequency. It has its natural dynamics, and it wants to move at that frequency. And if I'm moving it at that frequency in resonance, I hardly have to do anything to sustain that motion. I can make it move slower, but then I have to actively do most of the work. I can make it move faster. I can make it move faster, but again, that drives up my energy consumption. And if I just go with the flow, if I go with the natural dynamics, I hardly have to do anything, and I can sustain this forever. So you can interpret this figure as a resonance of the natural dynamics. If you're moving at a certain speed, yay, I use the resonance, I minimize my effort. If I go faster or slower, I have to put in more effort because I cannot use the natural dynamics as well as before. Now, the cool thing is that I have these different modes. And I'm running out of resonance in one case. Right? If I keep walking, I would increase my energy consumption, and I couldn't increase my speed anymore. But at that point, I switch to a different gate. I use a different oscillation mode. I get a different case of resonance, and I can minimize my energy consumption again, and then I do this again for galloping. It's almost like you're driving your car, where you're switching gears as you accelerate, right? You also do that to minimize your energy consumption. Otherwise, we would just drive in first gear all the time. But as you accelerate, you switch from one gear to the other. So having different gates exactly is the same thing, right? Switching gears to minimize energy consumption. And that is pretty awesome, right? And it would be fantastic if we could do that with a robot. And that basically describes, if I would have one sentence to describe my research goal or my research effort, it's that. I want to figure out how this works, and I want to implement it in a robot. If you're trying to do that, you have to build your robots differently. Traditionally, these are industrial robots. This is how we build robots for, 40, 50 years. We're trying to make them as stiff as possible. You have these structures here, right, that reinforce the robot arm to make sure it doesn't oscillate. We have extremely big motors with big gearboxes that make sure that gravity doesn't change the motion of the robot. So we always considered the natural dynamics as being our enemy, right? I want to do the same motion no matter whether I'm moving a 50-kilo motor block or whether I'm moving a 50-gram screwdriver to, mount that. So we were building robots to suppress natural dynamics. In walking, that's not a good idea because what you see in walking is periodic, and if you'd want to do something periodic, you should go with the flow. If you don't go with the flow, you're constantly accelerating, decelerating, accelerating, decelerating, and that drives up energy consumption. It's a little bit like driving a car in stop-and-go traffic, which means, overall, we have to build our robots like the leg shown here. And that's what I did during my PhD. We developed a full series of robots, starting with a single leg where we had a rubber elasticity in here. That didn't work out, so next year we built a quadruped which had springs down here. We called it ALF. ALF is a German acronym. It stands for Autonomer Laufroboter mit Federn, Autonomous Walking Robot with Springs. Didn't work out. That's why we called it ALOF, in German Autonomer Laufroboter ohne Federn, without springs. And then our advisor got really mad, and now we always claim it means autonomous locomotion on 4 legs. We tried a new approach. Now we have steel springs here. There's another spring hidden in the shank. That went slightly better. Updated version of this, and then this was kind of the 6th prototype of a single leg that went into Starlet, not ALF, our latest quadruped. And I want to show you a video of what, it summarizes in about 5 minutes the work and the idea that goes into the development of this robot. And it doesn't focus as much on energy, but you can imagine that having something soft, something compliant, something that adapts to the environment, something that allows you to, to react to disturbances, that allows you to do force control, has also a lot of practical implications. And this video will, highlight these practical implications.
In this video, we want to show you how to design, build, and control a 4-legged, electrically driven robot. The goal of our research is to make such machines robust, versatile, fast, and energy efficient. Before discussing robotic devices, let's have a look at nature. This is a dog called Rocky. He has 4 legs attached to a main body, each of which allowing movement in all directions. To do this, he needs control of at least 3 degrees of freedom. Using this as inspiration, we designed the leg with a similar kinematic structure, driven by a set of electric motors, which collectively allow actuation of the required 3 degrees of freedom, namely hip abduction, hip flexion, and knee flexion. Mounting 4 of these legs, additional motor controllers, and onboard computers, we get our first quadruped robot, ALOF. To make ALOF walk, we have to coordinate all 12 joints correctly. Firstly, we have to keep the center of gravity over the support polygon to avoid falling or tipping over. Secondly, to ensure forward motion, the feet have to step ahead accordingly. The onboard computer calculates the desired joint position using inverse kinematic methods and sends them to the motor controllers several hundred times a second. The motor controllers can then precisely track the joint positions over time. With his joint mobility, there are many other things ALOF can do. He can stand up, recover from a fall as a result of tipping over, and even move on steep inclinations or loose ground. In this case, he applies a special turtle-like crawling gait. All these maneuvers are relatively slow and thus created prior to application. In this state, ALOF is not programmed to react to unforeseen events. Additionally, since the robot is designed mechanically stiff, it behaves more like a table than like a dog. The rigid characteristics are further exposed if ALOF is subject to impact forces. The peak loads occurring due to the ground contact interaction immediately destroy the gearboxes. How can we engineer a robot that interacts with the ground similar to a real dog? To analyze this, we first have to understand the actuation principles in and around the joints of legged animals. The rigid links, in this case bones, are manipulated by a muscular tendon system. In contrast to standard robotic devices, both muscles and tendons act as compliant elements, sustaining large impact forces and storing potential energy whilst falling or running. This then allows the animal to interact in a compliant way with the environment and locomote very efficiently. While the leg is compressed, energy is stored in the muscles and released again before liftoff. To adapt these mechanisms to a robot, we had to rethink the mechanical design. Instead of connecting the motor and gearbox directly to the link, as done in Olaf, we included a spring in series. This is called a series elastic actuator. Similar to nature, the spring protects the gearbox from impact forces and allows for energy storage. Measuring the spring deflection and applying Hooke's law, we get precise information about the actual joint torque. By moving the actuator correctly, the actual joint torque can be controlled. Based on these principles, we built a new quadruped robot with steel springs in all 12 joints. All the actuators are tightly integrated at the hip joint to make the moved segments as lightweight as possible. The low inertia at the end effector allows fast leg motions and reduces impact losses. This new robot is called Starlet. Let's go back and drop some dogs. Okay, the robot doesn't break. Instead, he passively bounces around due to the mechanical springs, something we don't see in the natural counterpart. To mitigate this bouncing, Starlet has to be controlled continuously throughout the whole drop. Let's have a look at this process in detail. First of all, we have to detect contact. After making contact with the ground, the joint angles, body acceleration and rotation rates can be measured. With this information, the base position can be precisely estimated. To control the robot, we virtually apply forces on the main body. This allows us to imitate the required dynamics needed to stabilize the robot's orientation and position. These forces are distributed to the contact points and subsequently to the individual joints. Applying this principle, we can achieve quite natural behavior. Starlet can react to lifting its foot and pushes. Furthermore, we can start to become more dynamic and fast in our maneuvers. As an example, Starlet can perform a trotting gait. He can do so even if there are obstacles in its way. In such maneuvers, the spring in series contributes to the passivity of the system. The springs in the joint are compressed after landing to store energy and released again before liftoff, increasing the running efficiency. Despite all these efforts, there's still a long way to go until legged robots will support us in our daily tasks.
This is 90% engineering, right? And this is more as a backstory, right? During my PhD, that was my goal. I want to build a quadruped that walks. And about 80% of my effort went into this. You have to design the system almost like an airplane. It has to be super lightweight because there are these airfaces, right? You want to make it run. So if you make it heavy, your actuators have to be bigger, and then it gets even more heavy. So you always right at the limits of what your hardware can do, right? You call up your motor manufacturer, you say, hey, you say you can produce a Newton meter of torque. Can we can we get 2 out of this? How much can we get out before the motor burns? How much can we get out of the gearbox before it collapses? So you're always playing with these limits, and it took, I always say, about 80% of my time of my PhD to get this done. The remaining 20% of the work are then the science, some of the things that I showed you today. The 80% work that went into this made 5 pages of my thesis, right? The other 95 are about the science. I failed, right? I never got, or at least, well, we were a team of about 5 people by the time I left, right? We never got the robot to work while I was there. I left ETH in August 24th, 2 years ago. And we got close, but we never quite got there. I had to go to Michigan. I started my appointment here. 2 days later, my colleagues sent me this video and with this original soundtrack.
shouldn't have been a messin'. And now someone else is getting all your best. These boots are made for walking, and that's just what they'll do. One of these days these boots are gonna walk all over you.
Of course, I'm still trying to build robots. I had to put together a lab and trying to put together a new robot. This one is called Ramon, so this is the robot that I now have in Michigan. It's a bit simpler because I have a smaller team, right? I don't have 5 people working on this all the time. So it only has 2 legs. And as you see here, it's mounted to a motion planarizer, which makes sure that it can only move in what we call the sagittal plane, so it cannot fall sidewards, it cannot turn sidewards, and all that makes the control a lot easier. You also see that I have 1 set of clothes. And this is essentially the research that I want to do here in Michigan. I want to keep doing over the next couple of years, explore the ideas that I shared with you today, which were all based in simulation, explore them in actual hardware, and trying to get closer and closer to what horses can do. And as I said before, this is incredibly useful. If you think about it, between 0 and 7 meters per second, by choosing the right gait, horses can have almost the same energy efficiency. They're equally efficient at moving at high velocities as they are at low velocities, and creating that in robots would be an extremely desirable goal. In the process, we will learn a lot about biology. We can learn a lot from biology, but we also have to do a lot of engineering, designing these machines, controlling these machines, powering them, putting in good actuators, and all the stuff that I just was able to kind of highlight in this short 5-minute video. And coming back to this question, what was there first, the curve or the preference? Right? For an individual horse, we solved that today. We said, well, these lines, they're based on the natural dynamics. If you move at slow speeds, sort of these medium speeds, you can reduce your energy consumption. If you increase your speed or decrease your speed, your energy consumption goes down. So from that, goes up, I'm sorry. From that follows that you should only locomote at this speed. And if you're at IKEA and you're not locomoting at that speed, your energy consumption goes up. You need more meatballs to fuel up again. If you think about this not for an individual horse, but in terms of evolution, right? The way horses were designed over millions of years. And if we're building a robot, we're essentially trying to replicate that process. I want to design a robot. You actually can turn it around. This is super useful. I have a slow, a medium, and a fast velocity. And they all have the same energy efficiency. So somehow, right, and it's of course not the only thing that went into the evolution of horses, but somehow their locomotion apparatus, the stiffness of their springs, of their tendons, the mass distribution, leg length, all of these factors, right, they influence the natural dynamics. They influence the mechanical dynamics, and the mechanical dynamics influence the locomotion of these minima. And you can imagine that all of these are in the same place, and that wouldn't be very useful. You saw in what I showed you with our models that galloping never was efficient, but had a curve somewhere here. So it was basically us wasting a gait. So if you think of this not in terms of control, but in terms of designing a robot, in terms of replaying evolution, you actually have to start with what should the robot do? At what velocities should it efficiently locomote? Think about, for example, a search and rescue robot. You know that thing has a sensor that's trying to detect victims or injured people. That sensor can only be moved along with a certain velocity. You don't want to go slower because you don't want to waste time, but you can go faster because then the sensor cannot resolve what's going on. So this is given, your walking velocity. And so you can design or can try to design a robot that is specifically tuned through its natural dynamics to locomote at that velocity. That would be cool. But then, that robot has to get there and has to go back. And And of course, you don't want to do this at the same speed. Now the sensor's off, you're not looking for injured people. You just want to run back and forth as quickly as possible. So if you can get the robot to have a second locomotion mode, galloping or trotting, you have now these two different modes, and you can get it there quickly, then switch to an energy-saving gait that you can look for a very long time, and then go out quickly and maybe replace a battery or, I don't know, bring back a victim that you found. That brings me to the end of my talk. To summarize what we saw today, we looked at different gaits as they appear in nature. We looked at they come with different footfall patterns, that they come with different contact forces. We saw this M shape. We talked about that, we didn't know this for a long time, what these footfall patterns are. And then I spent a very long time talking about this experiment. And basically the entire talk today revolved around this Hoyt and Tail experiment that tells you so much about energetics and locomotion, particularly if you choose your velocity wisely, you're efficient. If you're forced to move at a different speed, your energy consumption goes up. We showed that this is something mechanical that we find in robots, and that it's driven by the natural dynamics, and that we can actually create all these gates completely passively. And then we try to build a robot that kind of resembles this, and this is shown here. And then, if you have a slide like this, you better stop. That's what I want to do. Thanks a lot for your attention. Do some references.